Hey everyone, Morgan here. So we're talking about light today. We're on page 10 of 14 of the lecture outline. And I'm starting out here with just some numbers to help you get a feel. We typically use nanometers when we're talking about the wavelengths of visible light. So 400 nanometers is equal to 4,000 angstroms. Very seldom does anybody use angstroms anymore, but just in case you come across it in some older literature, I wanted you to know about it. Basically, there's 10 angstroms in a nanometer. Now, this is equivalent to 4.00 times 10 to the negative 7th meters. And that is equal to 4.00 times 10 to the negative 5th centimeters. And a lot of the people that I knew in physical chemistry that worked with wavelengths all the time, they basically remembered this, and they didn't have to do unit conversions. They could just see the differences based upon this and do the conversion in their head. Okay, so now this is what the wavelengths are for a rainbow. And I need to point out that this is more of a suggestion than a rule. Violet does not just specifically end at 450 and blue start at 450. It doesn't happen that way. Remember that visible light is a continuous spectrum, and one color just bleeds into the next. Okay? So these are rough estimates. Now, if something is right at, say 425, right in the middle of that, it looks pretty violet. Okay? And here, 475, that would be pretty blue. Okay? Or maybe even a pretty blue. Okay, so now, when we talked about waves in the last few pages, we talked about how wavelength times frequency will always equal the same number, which is the speed of light. So let's see if we can't run a few of these through a calculator and show you that. I've got some violet light, 400 nanometers, or 4 times 10 to the negative 7th meters, and its frequency is 7.5 times 10 to the 14th hertz. So what I'm going to do is I'm going to put 4.000 second EE negative 7th and multiply by 7.500 second EE 14th, and look at that. I'm getting 3.00 times 10 to the 8th. For green light, 5.000 second EE negative 7th multiplied by 6.000 second EE 14th, and I'm getting 3.00 times 10 to the 8th. Actually, I could do it as 3.000 even. For some yellow light, 5.750 second EE negative 7th multiplied by 5.217 second EE 14th, and rounded off, that's going to be 3.00 times 10 to the 8th. Okay. Now, when I was in junior high, high school, all through, say, the 1970s, up to probably about 1987, there's this great radio station in Los Angeles called KMET. Now, its frequency was 94.7 megahertz, or 94.7 times 10 to the 6th hertz. Now, its wavelength was 3.17. Now, we don't identify radio stations in America by wavelengths. They do it in Britain, but not here. So let's see if the same holds. 3.17 multiplied by 94.7 second EE 6th, and there you go. All electromagnetic radiation travels at the speed of light. Okay, so now, some more typical questions. What is the frequency of some green light that has a wavelength of 5.25 times 10 to the negative 7th meters? Well, I know C equals lambda times nu. I'm trying to find nu frequency. That's lambda. Nu equals, okay, and that is going to be C divided by lambda, which is 3.00 times 10 to the 8th meters over seconds, divided by, put it over here, 5.25 times 10 to the negative 7th meters. Meters cancels meters. I have 1 over seconds. A lot of people call that hertz. I'm pretty happy calling it 1 over seconds. That way you see how to cancel units. So 3.00 second EE 8th divided by 5.25 second EE negative 7th equals, and I'm getting 5.71 times 10 to the 14th. Now, I know just from my experience working with these numbers for all these years that that is the correct magnitude for the frequency for some visible light. Okay, so now how about some radio waves? What are their wavelengths? So I'm looking for lambda, and that is its frequency, nu. So if C equals lambda times nu, nu equals C over lambda, or lambda equals C over nu, which equals 3.00 times 10 to the 8th meters per second divided by 9.55 times 10 to the 7th. Now hertz is a 1 over second, so I can do that as 1 over second, and seconds cancel. And this is going to come out in meters. So 3.00 second EE 8 divided by 9.55 second EE 7th. Yep. Equals, and about 3.14. Here in Los Angeles, that would actually be KLOS, 95.5 megahertz. Okay, now, energy of a photon, energy E equals h nu, which equals, and the value for h, which you'd always be provided, is 6.626 times 10 to the negative 34th joules times seconds multiplied by, now I need to find the frequency. Okay, if C equals lambda nu, nu equals C over lambda, which equals, and I'll put the 3.00 times 10 to the 8th meters per second upstairs, 475 nanometers. I'm going to have to do a unit conversion there. 10 to the 9th nanometers per meter. Okay, nanometers cancels, meters cancels. I'm in 1 over seconds, which is good. So let me do some math here. 3.00 second EE 8th divided by 475 equals, times, I'll do 1 second EE to the 9th equals, now I'm getting 6.3, we'll call it 6.32 times 10 to the 14th. 6.32 times 10 to the 14th. So we can multiply this by 6.32 times 10 to the 14th, 1 over seconds. Seconds is going to cancel, and this will equal, so that multiplied by 6.626 second EE negative 34, and I'm getting 4.18 times 10 to the minus 19th. Joules. Now, before you get a little freaked out saying, wow, that's really tiny, remember that's just the energy of 1 photon. Now, what if I had 10 photons of that light? Well, E equals N. Let me rewrite that. NH nu. I'd plug in 10 this time, so I just have to multiply that by 10. 10 times 4.18 times 10 to the minus 19th joules equals 4.18 times 10 to the negative 18th joules. So it's not that much more energy for 10 photons. But what about if we get to a whole mole of them? 400 nanometer light. Okay? Actually, you know, if I go back up to this table, the frequency is already given. It's that same number right there. But I'm going to do this problem a little bit differently. If E equals h nu and nu equals c over lambda, E can equal n, the number of particles, times h times c over lambda. Put all those things together. So the number of particles is 6.022 times 10 to the 23rd per mole. Okay, h is 6.626 times 10 to the negative 34th joules times seconds. And then we have 3.00 times 10 to the 8th meters over seconds. It's 400 nanometers. And oops, I can say 10 to the 9th second EE 23 multiplied by 6.626 second EE negative 34 multiplied by 3.00 second EE 8th multiplied by 1 second EE 9th equals, divided by 400 equals, okay, so 299,263. So we'll call that 3.00 times 10 to the, and I'll count over 1, 2, 3, 4, 5 places, times 10 to the 5th. All right. There you go, folks. That's page 10. Thanks for tuning in. This is Morgan signing off.